Hello, everyone, and welcome to our Digital Live, a podcast series by IEEE Signal Processing Society. Founded as IEEE's first society in 1948, the Signal Processing Society is the world's premier association for signal processing engineers and industry professionals. In this series, we'll be having candid discussions about the developments of various areas of signal processing, which are the underlying ubiquitous technologies for today's modern society. In this episode, we'll be discussing the AI revolution in the telecommunications sector with our guest speaker, Professor Mérouane Debbah, and our special guest co-host, Professor Samson Lasaulce. Welcome.
Hello, everyone. So my name is Samson. Today we'll be discussing the current and future impact of AI, and more particularly large language models on wireless networks. So it's my great honor to introduce you Professor Mérouane Debbah, who is with Khalifa University in Abu Dhabi. So Mérouane, would you mind introducing yourself to the audience?
So thank you, Samson, for having me in the show. So my name is Mérouane Debbah. I'm professor at Khalifa University and director of a 6G center since 2 years. And I've spent much, I would say, of my career at the intersection of advanced wireless communication, mathematical optimization, and quite recently, machine learning. And over the years, what makes me very special is that I had the privilege of working both at academia and industry, moving back and forth in positions of professor at university, but also taking leadership roles in various companies. And this is basically ranging from leading mathematical and research algorithmic labs to also co-founding research initiatives on AI and wireless systems. My primary focus of research has been on leveraging mathematical tools to design networks, and mostly rooted in the field of two fields, one called random matrix theory and the other, I would say, large-scale optimization. And game theory is one of those, and I think Samson, you are the expert in that. Recently, I've been quite involved in the intersection of generative AI and wireless, and this is, of course, the purpose of our talk today. And also building teams to be able to harness what we call LLMs, large language model, for communications and also networking challenges.
Thank you, Mérouane. So to get started on AI for wireless, let me ask you about the history of, say, machine learning, deep learning, say AI in general, for wireless networks. What is the history?
I think the field of wireless communication roots back quite very far, in fact, not just the 1990s, because there's been already a lot of results using neural networks in the 90s in communication. But I would put it back in the 1948s, basically with the two key, I would say, leadership and scientists who brought the field of information theory and what we call control theory. In the field of information theory, of course, the way you compress, there's a lot of machine learning. It's based, of course, and if you take back to Shannon's point of view of counting the alphabets, well, basically that's already big data, because then you look at what we call some kind of joint probability distribution, and you try to learn that after the letter Q, there's a Q. This is called Markov chains. And we've been using all these tricks since many years. At the same time, when you think about basically control theory, that's also about an issue around machine learning. The idea of Wiener in 1948 was to say, well, if I can't have a model basically of my medium, then what I'll do is replace it by a black box. And what I'll do is try to minimize some outputs, given some utility that I will optimize. And with some reward function, at that time, of course, the output was what we call the MMSE. You'll start learning through a bunch of iterations how basically to leverage your input so you can get your output. So when you see the field that in which we've been working, it's been since 1948 where people have been using in some way or in the other ideas related to machine learning. And of course, as we all know, the godfathers of machine learning with this famous conference of 1956 turned out to have, of course, these key people that I'm talking about, and especially Shannon, who played a big role. Now, if we look at the modern machine learning aspect that we think about today, well, of course, it's more around the 1990s where we've been looking at what we call statistical signal processing for the use of channel estimation, interference management, and antenna design. And there, of course, we've been seeing a big progress, and especially then with the use of all these techniques basically to introduce machine learning, and especially what we call vector machines, support vector machines in basically the 2000. But classically, I would say what we saw is, of course, a big advancements around 2012, 2013, with the fact that compute power was over there, and where we saw many more, basically, of course, papers, but of course also some, I would say, proof of concepts using deep learning networks in the field of wireless communication to enhance basically the systems that we're having, and for which we think the future is about, of course, having these devices which are optimized thanks to machine learning techniques.
So yes, thank you, Mérouane. So you have been mentioning, say, this milestone, say in 2012, 2013, as you said, with this, say, emergence of deep learning, because it was out there, and so it started to deploy. So could you give us like a concrete, say, a list of concrete applications of deep learning? Say classical deep learning, not generative. We'll be talking about generative AI after. So can you give us a list of concrete application of deep learning in wireless networks?
Okay, so the first, of course, example that came to the people was to understand better how to use, I would say, deep neural network for what we call self-organized networks, which is a concept that dates back to 2008, related to the deployment of a technology called small cells. And in that realm, of course, a lot of people were a bit trying to solve the problem of what we call dynamic spectrum management, which is basically the fact that whenever two devices tend to choose the same kind of band, then there's a collision and then the transmission does not work. And in that setting, of course, it turns out that it's quite hard to model basically the whole system in terms of interaction. And there what we saw is, of course, the use of deep neural networks basically to optimize this kind of dynamic spectrum management in terms of choices of bands and in which you're gonna move on. And of course, you can go from centralized to decentralized. And we've been seeing a couple of very interesting work trying to do that. The second thing also that we saw quite rapidly is, of course, the efficient use of these techniques on what we call end-to-end optimization of systems. In wireless communication in general, we can model quite nicely some parts, typically the channel, typically the equalizer. But whenever we tend to model basically the end-to-end metric, it tends to be quite complicated. And we've been seeing a lot of work using what we call an autoencoder approach, where we try to model basically the system as an end-to-end. Non-linearities typically at receivers are extremely hard to model. And so what people tend to do basically is to look at the system as a black box instead of modeling each part, which tends to be quite complicated, especially as I said, when you have, for example, nonlinear amplifiers that you need to take into account. So it was mostly on the modeling perspective that we decided to go and depart from that to go to a data-driven approach and use, of course, deep neural network to be able to transmit information from one point to another point, basically by modeling, by data-driven approach. And deep neural networks with autoencoder turned out to be quite good. At this stage, as far as I know, I haven't seen a product designed by that, but we're seeing a lot of experiments showcasing, of course, the benefit of using this technique, especially when you're not able to model a lot of different aspects. The third one also is related to what we call default detection and network diagnosis. In general, basically, that's extremely complicated to know when an error happened in a system. And this is where also deep neural network turned out to be extremely fruitful to detect those basically fault detection that you have in the system. We have also basically a lot of people today trying to see also how mobility management could be exploited using deep neural network. As you know, you need to predict in the case of mobility where the user movements and how you can pre-allocate resources to improve the quality of service. And for that case, we worked a couple of years ago during my time in industry on looking at how we could pre-cache information basically to send, especially when you go in tunnels in different regions. And this requires a bit of predictions. And the prediction is based, of course, on the data routes and the traces of the different users. And by that, of course, you can pre-allocate resources, you can pre-bufferize resources, you can pre-store resources in a very efficient way. And so in these three examples that I've been giving, there's another number of plethora, but those were, I would say, the most for me interesting, which had some direct applications. I could talk about, of course, how you would use these techniques to do interference cancellation when basically you can't model the kind of noise that you have, channel estimation. But those examples that I gave you, I thought I think are the most interesting from my point of view.
And among all these, say, applications of deep learning you have seen, is there one, I think, which surprised you, that would say, which allows to change the paradigm? For instance, you have been mentioning, okay, dynamical spectrum management, etc., and coding, end-to-end coding, decoding, etc. But is there, like, I don't know, some a problem at the physical layer or at higher layers for which really deep learning has given something new?
Yeah. So for that, yeah, there was some hard work that we did a couple of years ago related to what we call basically AI-based localization. So I'll explain quite rapidly what I mean by that, and for which basically AI turned out to be extremely good. So you have to know that the people who have built 4G basically have designed 4G as what we call a kind of a full IP type of network. What it means that basically it's an internet protocol that you're designing. And in 4G, voice is not an application, is not a technology, but an application. Okay. And what I mean by that is that it's extremely hard to improve the voice quality on a 4G network. By the way, when we deployed the first 4G networks, 2G in terms of calls was much better than 4G. And it makes sense because in 2G, voice is a technology. In 4G, basically, it's what we call voice over LTE, which is a full type of IP network. And why it turns out to be extremely complicated to improve the voice quality basically in 4G is that there's a whole bunch of protocols which are embedded in that. It's not just about having more bars on your phone, which makes that the quality of the call is better. But in general, basically, there's also IPsec protocol. So it's an end-to-end metric. And so in that example, I'll talk about the AI-based localization. We were asked a couple of years ago to improve the quality of voice over IP. And what we realized is that even if you improve the SNR, it doesn't matter because what counts is the whole system. And so what you need to do is then try to model the whole end-to-end quality of experience in a voice scenario. Mathematically speaking, when you write it down, it's extremely complicated to write it down. And I think the colleagues who are hearing me right now, who are more physical layer, they can model basically an SINR. But in general, when they need to model the whole protocol stack, it turns out to be difficult. And this is where I was surprised that during 2 years, we were stuck. And we had the opportunity to get access to some data of an operator for different basically base station deployment and different basically quality of service of voice in a 4G LTE. And quite surprisingly, by using that data, which I thought would not work, it turned out that we could basically construct and learn what would be basically the kind of allocation of resources we should do to improve the quality of service. And it turns out that that approach, which is a full data-driven approach, turned out to have basically improvements of up to 40 to 60%. Whereas looking at modeling and spending our time with team turned out extremely difficult. This example that I'm giving you, we of course translated also to the issue of what we call localization, for which also basically it's quite complicated. What I mean by that, localization today is based on triangulation of base stations, and I think my colleagues are familiar with that. But that works quite well when you are in a line of sight environment. Where in your non-line of sight environment, it gets difficult basically to position a device. But that's where techniques like fingerprinting play a big role. So what is fingerprinting? Well, basically, you have a database where you measure basically the impulse response and the position. And so you have a database of a lot of positions and a lot of impulse response. And next time, basically, you measure an impulse response, you're requested basically to know where the user is. And it turns out by using basically deep neural network, we're able basically, and we did some experiments showcasing that this works. And what's even more interesting and even worse when you have some changes of environments. And basically for that, we need to use techniques like persistent homology and things like that. But just to give you these two examples were quite striking for me on one, not being to model. Second, having no clue on how to solve the non-line of sight in case for AI-based localization and for which an AI-based approach turned out to be good.
Okay, thank you very much for these very convincing examples. So, Mérouane, you have been an expert in wireless communications for your whole career. You have been working on 4G, 3G, 4G, 5G, 6G, maybe 6G, 7, 8, I don't know, okay? And it turns out that, say, more than 4 years ago, okay, you, well before LLM became famous to the general public, okay, you decided to build a team focused on large language models. So how did you come up with this idea and what was your vision?
So that's a very good point. So I would say in 2019, I grasped basically one of the key papers, which is quite known, called "Attention is All You Need," and that paper, of course, struck me because a lot of people put LLMs with basically the release of ChatGPT in 2022. But if you were in the domain, basically GPTs were already there, and the transformer architecture was released in 2017 in a paper. Of course, I didn't catch it up in 2017, but already in 2019, basically I grasped that paper, and I was quite struck basically by the capability with transformer to basically deal with unforeseen tasks. So when I came basically with that paper, of course, the idea was to start looking at what you could do with that. Initially, of course, the application of telecom and wireless did not come to my mind. It was mostly about looking at how these large language models that people are talking about and GPT architecture based would be able to basically tackle unforeseen tasks on the fly. And my idea, of course, when I came to the UAE was to kickstart basically some activity related to basically trying these techniques and trying to build these techniques related to large language models in Arabic and with a model called Falcon, which turned out to be a big success. So my initial goal was not directly to build up something related to telecom initially, but progressively when I started building these models, especially basically for the Arabic and the language, it turned out that for me, the kind of language that we're talking about can have a lot of modalities. And this is where, of course, it struck to my eyes that immediately we could generalize these kind of models to modalities which are quite tailored to the telecom domain. The telecom domain, what kind of modalities we're talking about? We're talking about radio frequencies typically, on which you would like to build something like an RF GPT. And so this is how it started, basically building the whole team, which turned out to be quite successful in building a couple of key models here in the UAE. I have to admit that we were quite lucky in taking things in advance, as you said, because when we started basically building the team, that was in 2021, early enough to start building the team and working on it. And having also the vision that that kind of, I would say, prediction of the next token could have such an impact in our industry was something, of course, that I saw quite rapidly, just because basically there's a lot of commonalities basically in language that we did with Shannon about how basically you construct a sentence by looking basically of how you predict each letter afterwards and making your compression scheme. And so coming back to quite rapidly to why I, in 2019, thought about how you could go forward, well, for me, it was evident that beyond prediction, beyond going into basically tackling unforeseen tasks, LLM is nothing else than a compressor. And so it was obvious that since large language model could compress all the data with a model, which had a sufficient number of parameters. That is exactly at the heart of what we're doing, Samson, about Shannon theory. And so it was very obvious for me that that was a great domain to work on.
Okay, great. So now, okay, you're really involved in applying LLMs to telecommunication. Could you tell us what's happening there? So currently, what's happening there? And since you're expert in 6G, you are the head of 6G lab, how will LLM help and be implemented in 6G?
So very good question. And I get this question many times about basically the connection of LLM and 6G. So if you look at the history of cellular networks, typically, since we're talking about 6G, we've been going through what we call generations: 2G, 3G, 4G, 5G, and today basically 6G. These generations have been going on a time frame of roughly 10 years. In the 1990s, of course, we started 2G with some KPI, which was mostly tailored for what we call mobile for voice. Okay, the capability of having this seamless kind of opportunity to phone anywhere in the world. 3G came in with the will to provide mobile for data, and I think we all remember the dongles to download data. 4G came in 2010 with what we call mobile for internet, having a wireless ADSL experience with mobility outdoor. 5G, which started in 2020, was mostly tailored for basically the mobile for things, or the IoT. It turns out that today, even though we have some deployments of 5G, it's mostly the broadband feature, meaning having more rate of 5G. We're still not seeing things, IoTs, being heavily using 5G. And roughly this is a reason of mostly how you make money out of 5G. But what's interesting today is that AI is becoming very, very, very pervasive. And what we're looking at today with 6G is basically on how you connect intelligence, which is basically the fact that we're seeing a world where we're going to have a massive number of AIs which are deployed, and these AIs are going to be talking to each other. And of course, if you do that, it changes totally the realm of how you communicate with classical systems. Let me give you two examples for that. The first example is basically the fact that if you want to send a file from one point to another point, and I think people have been doing that, what you usually do is use some compression scheme, typically zip file. So you take your file, you zip it, or your image, you zip it, you send the data zipped, and then you dezip it on the other side. But if you start having LLMs on each side, and I take this example for a reason, what will you do? So suppose you have a chat GPT talking with a Falcon or a Claude from Anthropic. You would do image to text, if it's an image, or video to text. You would send not anymore basically the compressed image, but you would send the prompt. And on the other side, you would do text to image and you can generate it. Said that, it seems very easy and you could do it in any network. The problem, and I think you've been working on that a lot, Samson, is that if you do that, you're not able to recreate the same image on the other side, because it depends really on the model that you have, and basically, of course, the what we call the kind of background knowledge. And so basically, for that, you're not able to ensure perfect recovery. You can ensure basically some kind of common understanding. You can ensure that the meaning has been going on. And so you need to find a way on how you can build systems on which basically the meaning basically is kept without perfect reconstruction in the world of AI. This is opening doors, by the way, on a realm of research called semantic communication, and we're seeing a lot of work being done. The second thing also, which is interesting on that, is that we are now having not anymore a one single colossal AI which is being built, but basically a network of AI. And if you have a network of AI, this is called a network of agents. These network agents basically start collaborating in some way to solve some tasks. And that is quite interesting because we're also coming back to basically providing the opportunity to connect these different intelligence to start basically doing some things jointly in terms of solving a given problem. Let it beamforming, energy efficiency of a network. And the fact that you are making these systems interact is also at the heart of what we're working up today in terms of 6G. That's basically, I think, the two main points that I think are quite important and big changers is that we're providing basically a network of what we call mobile for intelligence. There is a massive number of AI on how basically the systems are built, and then we need to build the network. Of course, this creates a lot of issues, to be honest. On the first example, the definition of how you build a network where AIs communicate and basically how you build a semantic system. Second is when they start interacting, well, basically you need to be able to analyze the behavior. We're seeing a lot of work on game theory, distributed optimization, on how these systems will behave when they are totally decentralized because you can't centralize, and all other aspects related to that.
Okay, thank you very much, Mérouane. It's very clear. But I also know, and this is especially useful because we have some people who are experts in signal processing, and I also know you have some papers on, say, RFGPT, where you're using like LLM or multimodal LLM for, say, signal processing problems. Could you say something, say, like make a brief comment on this?
So thank you, Samson, for the question. And I wanted to insist on one aspect at the beginning because you asked me about LLM, not LLM and telecommunication, but LLM and 6G. And so what I wanted to talk at the beginning when I talked about that is, of course, how LLM basically and 6G are intertwined. And the idea is, of course, that they're intertwined because 6G is about building the network of LLMs or the network of AIs. Now, the second aspect that you're asking me is even more interesting, is about, of course, the application today that we're seeing about LLM for telecom and not telecom for LLM, because the 6G and LLM that I was talking is about more telecom for LLM. What telecom can bring to the world of LLM. And this is exactly what it can bring, is basically providing the network to interconnect them. On the first one, which is basically what LLM can bring to telecom, which goes beyond, I would say, 6G, could be applied to 5G, it could be applied to 4G, it could be applied to Wi-Fi, it could be applied to many of the systems that we have designed and the ones which will come in the future, correspond, of course, to build models, first, that can optimize the network. And second, models which have basically the ability to capture the multimodality. We'll talk right now about the example you gave me of the recent contribution we did with RFGPT. And the third one is also working on basically LLMs, which can be embedded in devices. So let's go on the paper first that you were talking about, is basically the fact that we realized quite rapidly that there's no reason in telecom domain to just focus on languages. You can focus on things which are more of the RF type. And the work we've been doing is to start basically integrating basically radio frequencies and to start playing with those radio frequencies to do things like RF to image or even RF to video. It's not in some sense a crazy idea because a radar, that's what you do in general. You measure signals and you try basically to reconstruct the airplane that you saw. However, with these large language models, if you have a lot of data corresponding to different environments, typically that you have in terms of houses, whatever, and a lot of RF measurements, then of course you can embed that to construct basically a system or a multi-model model so that you could do this RF to image or image to RF. The fact that you can embed that in 6G becomes more interesting only because the kind of frequencies that you deal in 6G with becomes more interesting. What I mean by that is, as you may know, 6G has frequencies which go much higher than the classical, I would say, C-band or sub 3 gigahertz band. And so by going in higher bands, you can get much more granularity in terms of what you can see. And so in terms of applications for sensing, I strongly believe that the capability of these AI to integrate basically those signals out there is going to be instrumental in terms of reconstructing and to do what we call 3D imaging. And so this is the kind of work that we did recently, and I think this is going to open some major doors in the field of 6G related to sensing. But again, you could do that in Wi-Fi, as I said. However, the good part about this is the fact that 6G frequencies provide you basically the kind of very low, basically, wavelength, which guarantees you basically some kind of granularity. And the second thing which I wanted to talk about is also the fact that we as engineers are also basically working today on providing and making sure those AIs can run on devices up to the IEEE. This is what we call in the edge. And I'm talking here to all my colleagues of the SP field. What we realize is that if you decide to bring basically an LLM on a device, it becomes extremely complicated. You have two approaches. One approach that you can do is take a model which is big and quantize it. This is called post-processing an LLM to make it small. Another way would be to take and train an LLM by taking the low precision of your hardware that you have, just like the people who are doing 1-bit quantization for MIMO, and basically to be able to build a model which takes into account the constraint that you have in your hardware. This is called binary neural networks, and you can, of course, extend it to quaternary neural networks. What we realize is that the people working in the SP domain are very good at that. Why? If you decide to train your neural network by constraining your weights, by taking only values which are 0 and 1, then you can see the problem of training, which was initially is an optimization problem. Because, for the colleagues here, when you do training, it's optimization. Optimization requires a gradient. And the classical algorithm that we use is what we call a gradient descent or a stochastic gradient descent. But now if you want to train and your weights can only be 0 and 1, it becomes combinatorial optimization. And so combinatorial optimization becomes a decoding problem. And so all my colleagues who have been working in decoding turn out to be having the right skills to build basically these LLM on device. And it's opening new doors basically for people to come up with new ways to do the training and up to, as I said, to the IoT level. So this is also quite interesting, basically kind of venue that I think is going to be. And the third part on which maybe we'll talk afterwards is, of course, LLM are also, and Sonso, you've been doing, and I'm happy that you're interviewing me, you've been doing some outstanding work, are also considered as what we call optimizers. And so a lot of the features that we have in telecom, again, not necessarily 6G, this is what I want to ask, I want to answer that in your previous question, but Wi-Fi are all related to optimizing energy, optimizing efficiency. And so what we realize is that also you could use these LLMs in a language format to provide in a language format what you want from the system, and where this language will be translated into a mathematical formulation. And then you have basically some specific models which are trained to identify basically the constraints. And then you have a bank of solvers to do that. And I think this is, from my point of view, one of the most important work I've been seeing so far about using these large language models to start basically optimizing our networks, either in a centralized manner, meaning having one, or having basically, as we talked previously, many of these LLMs interacting to solve a problem.
Thank you very much, Mérouane. It is very interesting, and I think it will be very useful for all people will listening this podcast, because essentially you have been saying that LLMs can be seen as compressors, so they are useful to compress signals. Then you have been talking about how compressing the LLM models, and for this you need like tools, like of course like quantization, like even ROSI and lossless source coding. And you also have this connection with discrete mathematics in coding. This is very interesting for everyone. So we are approaching the end of our podcast, Mérouane. So I would like to ask you, in fact, say two more questions. We know that predicting the next token is not always easy,
But still, how do you see the evolution of AI in wireless networks for the next decade?
Okay. So that is a very good question. So I think wireless is the right domain for making these AI evolving to what people call AGI or whatever. I still don't know the right definition of that. What I mean by that is that what we realized is that all the models that we've been building are trained on a massive number of data sets, multi-model if you want, and basically hoping that by learning on all these data sets, intelligence will arise. And the example that usually people give is if I take a kid and lock him in a library for 25 years, and in that library he reads all the book of the history of humanity, is there a hope that this kid who has only learned things on books and have seen nobody can become intelligent? What we realize is that it cannot be the case. And the reason is that interaction is very important. What it means that the models that we've been building so far need to have some interaction with their environment. And so in wireless, that's what you do. You build a network where things interact. And so the key component is how you're going to be able to ground those models that we've built so far to reality. And of course, sensors, from my point of view, are a key, basically, enabler for that. And so the capability to connect these models to the environment through sensors will be key, basically, to upgrade these models to a certain level, which will make them acquire more capability than what we saw so far. And so I think the big, of course, leap that we need to do is first that understanding how we can go on beyond the transformer architecture, which has mainly been built about what you said, predicting the next token, to an architecture that could, of course, learn from all the data that it's poured, but also from its interaction on the environment. And those interactions are based on sensors and interaction with other basic entities. And I think this will open the door to a lot of research. And of course, our positioning as people who are working in wireless will be instrumental in basically building the systems. So in the next 10 years, that's what I'm seeing at this stage is first, the capability to integrate sensing capabilities so that you can ground AI to reality and not just being only learning on textbooks or data that you've got over there. Second thing also, which is very also important, is that we realized also, and this is going to happen not in necessarily the next 10 years, but just in a couple of years, we've been realizing also that we are good at simulations, people who do wireless. And what we're seeing is that there's a plateau today related to what can be built basically on these models, only learning from the data. There's a kind of plateau where we have scratched all the data. And synthetic data has become extremely important to continue the progress. And the synthetic data is, of course, based on what we could simulate, and this is called digital twins. And I think the integration of those digital twins with data is going to be also a landmark in terms of movement on how you go. The third thing what I want to mention also is that all the ideas that I've been mentioning will not be realizable if we don't come up with what I called systems that can generate at the device or mobile level things at the speed of light. You remember the example I gave you on the transmission of a video from one point to the other point? That example, if you did it today, would require a lot of latency to reconstruct your image. And I think if you've been using ChatGPT, you see that it takes a time before basically you can generate, which requires what I call a number of tokens per second, which are generated quite fast. And the future is going to be, for me, about specific hardware, which can do specifically that task in a very good manner in terms of how you can generate a number of tokens per second quite rapidly with specific hardware which can be embedded on those devices. And I think if the progress can be made, we need to be sure that the latency of all these systems of interaction has to be compatible with the latency we've been seeing quite recently in the telecom market in terms of how you do transaction and all these aspects. And I think this is also going to be a big game changer in the next years.
Thank you, everyone. Thank you very much. My last question is would be like this. In your career, you have been quite often at the right time. For instance, you have been writing some papers on learning very long time ago, 2010, 2011, before people, meaning spend some time on reinforcement learning. You started Massive MIMO at the right time. You started RIS at the right time. So many things like that. And LLM at the right time. So now that's my question. What would be the advice, one advice or two advices that you would give to young students, like master student, PhD student, who wants to do his research career in signal processing?
So that's a very good question, and I get it many times in different settings. I think the first thing that people need to focus on is on the fundamentals, because a lot of people think that by scratching the surface, you will get the results. Of course, you can always get results at the beginning by scratching the surface, and you get a couple of bunch of publication. But it turns out that what is instrumental is having some solid grounds, and especially some solid mathematical and physics grounds. I think those are the heart of basically creativity, to be honest, in the sense that basically you can come up with some new toy examples, some new ways of looking at the problem, which is not the classical way. And I think a lot of the SP students that I see think that, I don't need to go deep, and I'm just gonna write the next paper by doing the simulation. I think what you need to come up back with is on mastering some important tools, and the tools are at the heart. These tools are quite important. I think there's a plethora of very important mathematical tools on which you need to work on and master to be able to be creative. Now, in terms of research, I think one thing that and I've been applying this philosophy to me every time, is that in research, there is what we call a comfort zone and then basically a risk zone. You have two approaches to do research, is to say, I'm going to stay in my comfort zone and publish the papers. But at the end, you see that at one moment, you're not going to progress. And then the other approach is to say, I'm going to go in a risky zone and basically jump on topics, which basically is high risk, high gain. But then if you do that, if for some reason, basically you fail, then of course it fires back on you, and especially if you're faculty. And my strategy has been always to work, I would say, in parallel on two topics. What I mean by that is, the comfort zone does not request so much effort for you. Once you start working on it, well, basically you start implementing it, and you know that you're going to get basically the results. It's quite predictive. Somebody has to do it. It's not necessarily straightforward, by the way, but somebody has to do it. But you know you're going to be doing it. If you spend the time, you're going to do. But while you're doing it, you kickstart exploring some domains which are risky, which enables you to still stay in the community by publishing, by going to conferences, while you start looking at other domains on which you think you start working and digging hardly on that. Once you see that the domain you chose start to be, I would say, well-designed, you start understanding well, then that's when you can depart and move on that train and kickstart basically the work that you're doing and moving on. And the same thing, once you move on that, then you can go back to another domain. And that's what I've been applying quite repetitively every time. As you said, while I was working on Massive MIMO, I was exploring other fields. Massive MIMO became a zone of comfort where there are a lot of problems, of course, and you need to work it out. And I started working it out, but I knew that I would get the result. And so while I was doing that, I was exploring quite already in 2012, 2013, some other domains. And in that example, I can tell you what happened is that while I was working on Massive MIMO, I knew that there's going to be like 5 years of intense research starting to 2012, on which, I need to figure it out how you could do it in FDD mode, what are in the cellular setting could happen. I started looking at other domains. And one of the other domains that I captured quite fast was basically what we call large intelligence surface. Large intelligence surface, in my case, did not happen like that. It happened again by, while you work, you open your eyes by talking to many people to understand what's happening in other fields. And one of the fields that caught my attention was the field of acoustics. I had the opportunity while I was in Paris to interact with the team of Matthias Fink in SPCI. And that team was implementing a sort of, I say a sort of because that was not a sort of a large intelligence surface in the acoustic domain, meaning for acoustic frequencies. And immediately when I went and discussed, it was quite obvious to say, why are you just doing it at the level of the frequencies of acoustics? Why can't you do it in the telecom domain? The question was, well, it's very challenging on the hardware. And my answer was, well, if it's challenging on the hardware, let's first look at the fundamental limits. Let's look at basically the algorithmic case and what are the gains we can rip off. And if the gains turn out to be quite good, then we can think about how you can switch these devices at the speed of, I would say, megahertz, gigahertz domain. And this is how it went. And same thing for each jump. While I was working on LEAS, the question of what are the things that we could design in a different way, AI came in. And same thing, by the way, before Massive MIMO, I was working on things related to SUN. And I think you remember the time we were working closely on self-organized network and game theory. I was trying to explore what are the other things. And I think this is the kind of attitude you need to have some very strong fundamentals. There's a conference zone where you're going to be working and you have to take it and continue. And that comfort zone, you continue working on it and where you feel that you can do some achievement, and then be open to other domains. The guys in acoustics, for example, today you would ask me what would be interesting for me. I don't have time so much, but it's evident today that a lot of the things with 6G that we'll be doing are going into higher frequencies. And so if you go at higher frequencies, there's two ways. Is either start thinking of how to improve every time the system with the higher frequencies. But then if you're totally open, you would say, let me go talk to the optical guys. And in photonics, basically, we are in wireless starting to reach the guys who are doing photonics. Why don't talk to the photonics guys and tell them, why are you using techniques and why are your techniques and what are basically the limitation of your techniques to bring them down basically to the people who are doing RF. And then you can start building photonics, ADCs, things like that. So if I was basically going on this, I'm not doing it right now because I don't have so much time, I would start asking and interacting much more with the photonics guys and asking those questions about, in LEAS, they started with acoustics. You're doing photonics. How can you bring down basically what you did to the bands which are lower, and how we could use and start exploiting, adapt, and make breakthroughs in the RF domain with the ideas that you're having.
Thank you very much, Mérouane, for sharing this captivating witness, which in fact illustrates very well that you have understood this exploration and exploitation trade-off, and you have been applying it to your research life. Very interesting. So thank you, Mérouane, for answering all these questions. So we are now at the end of our podcast. So I wish you all the best for your research in Abu Dhabi and continue to make this breakthrough. We like them. So all the best to you, Mérouane.
Thank you very much. Thank you very much for interviewing me. It was a pleasure to interact, and also how much basically the work that we have been doing in the past has been also influential in my career.
Thank you, Mérouane.
Thank you for listening to this third episode of our Digital Life podcast series. And in closing, we welcome you to explore our other episodes on all leading podcast platforms such as Apple, Amazon, and Spotify. We further welcome you to watch our video version on YouTube at IEEE Signal Processing Society and on IEEE Signal Processing Society website. Until next time, keep learning and innovating. Bye-bye.